or truly anything that, well, that binds and substitutes variables. So of course, the goal of this talk is to hopefully convince you by the end of it that if you are to implement one of these, you might want to consider our library. But I'd nonetheless like to take a bit of time at the start to explore the idea behind the library. So this is exactly what I'm gonna do, and we're gonna see what's the idea. So for this part, we're gonna use everyone's favorite programming language, the Lambda calculus, and here you can see a Haskell representation of its abstract syntax. And already here we have a really important question to answer. How are we gonna represent variables? So the choice made by Rebound, and hence the choice we'll make as well now, is to use the Bruijn indices. Hence, we're gonna use natural numbers, but already there we have an opportunity for improvement if we use dependent Haskell. What we can do here is index our whole representation of terms by a natural number, which is gonna act as an upper bound on the number of free variables in the term. To get this idea to work, we use this fin n type instead of the nat type, which represents natural numbers, yes, but only the ones which are smaller than the index of the type. This representation might seem familiar to some of you, and actually you might have seen it maybe in the Bird and Patterson functional Perl from this very same Haskell symposium, albeit a few decades back, in the Bound library, which is based on this same paper, or finally in a number of Agda papers which use similarly indexed representations. So this representation here is fine, but before we move on, I'd like to do a tiny change to it. You might have noticed that in the abstraction case, because an abstraction is binding an extra variable, we need to increase the bound on the number of variables in the body of the abstraction. And what I'm gonna do here is factor this increase into its own type. Doesn't really change anything to the representation, but having a separate type will be really useful later on, so keep that in mind. So now we have a representation. So we can use it to implement something, and what we're gonna do now is an evaluator for the Lambda calculus. As any good interpreter, it's gonna take two arguments. One is gonna be an environment mapping every variable in scope to its value, and one is going to be a term that we are in the process of reducing to a value. The type of environments is going to be left abstract. The main thing we need to know about them is that we can look up any variable using this kind of bang operator and get a value out of the environment. The last thing I need to define now is our values, and because this is a pure Lambda calculus, we have only one kind of values, abstractions. And I like all of my values to be closed, so rather than saying that the body of the abstraction can contain any number of free variables, I'm going to use the bind zero type, meaning that there are no free variables in it. And here you can already see the benefit of indexing all of our types by a natural number. We have this extra type safety. As I said, we can force values to be closed. And in my evaluator, I can enforce that my environment maps every variable in my term to some value. Now onto the actual implementation. So the case for variables is easy. We just look up a variable in the context and return that. For abstractions, it might be tempting to say, oh, I just got an abstraction. That's already a value. I can just return it. But here, pay attention that the type of my eval function tells me that there can be free variables in my abstraction, and of them to be specific. And values should be closed. So of course here what we could do is implement another function which is going to walk through the body and replace every variable by its value. But we can be smarter than that. What we can do instead is change our type of values, not to be plain closed abstractions as before, but to be open abstractions with a closing substitution, promoting them into closures. And this way in my abstraction case, I just have to pack the current environment with the abstraction and return the whole thing without doing any more work. Finally, in the application case, we just have to evaluate both operands recursively, scrutinize the left-hand side, which is going to be one of these closures, unpack the environment, and if we extend this environment with a new binding for the bound variable that we're in the process of replacing by the right-hand side, we can just evaluate the body and with that, we have a perfectly functional interpreter for the lambda calculus. So as I said, it's perfectly fine, but I have two issues with it. The first one, it only works with open terms, closed terms, sorry. It might not seem like it, because my signature is taking a term with n free variables, but whenever I have such a thing, I have a closing substitution very close, so we do not really allow open terms. Second issue I have is that it doesn't really look like the lambda calculus, or at least it doesn't look like a research paper on the lambda calculus. If you read a paper on this topic, and more specifically about big step semantics for the lambda calculus, you'll find a rule like this, and you can inspect it as much as you'd like. You won't find any mention of an environment or a closing substitution in there. Which means that if you were to try to implement this, you'd have to put this extra effort and risk introducing bugs. So instead, we're going to try another approach. We are going to try to re-implement our evaluator, but this time following this rule to the letter and do nothing else. Hence, the signature doesn't take an environment anymore. It takes an open term and returns an open term, also solving my other issue. For variables and abstractions, there is nothing to be done. No reduction can occur. However, when we have an application, we just follow the rule. We evaluate both operands. We scrutinize the left-hand side, which is going to be an abstraction. And here, we do the reduction into steps. First, we use this instantiate function, which corresponds to the substitution. And then we reduce the whole thing. Of course, now I need to implement this instantiate function. There are multiple ways to do that. We're going to use one device known as parallel substitutions, which take every variable in the scope and replace it by a term in another scope. So these parallel substitutions are going to be represented using this env type, which is suspiciously similar to the environment from our first implementation. And with this device, how can we implement instantiate? Instantiate should replace the first variable, the bound one, by the argument and leave all of the others untouched. So we create a parallel substitution which does just that using this, can I point here? Yes, I can. This combination operator to replace the first variable by the argument and leave all of the others untouched, acting as the identity. So of course now I need to implement the substitution function, but this one is easy. Whenever we have a variable, we just replace it by whatever is in the environment. When we have an application, we apply it recursively. And in the final case for the abstraction, it is slightly more complicated, but not much. All we have to do is shift the environment around, as one does with the Bruijn indices, and apply this new shifted environment to the body of the abstraction.
What is IDs?
IDs is a parallel substitution which acts as the identity, not replacing any of the variables. Does that sound good to you?
So it's of type N or something?
It is of type env and n. It maps every variable to itself. So now we have another implementation, which again is working just fine, but we've introduced another issue here. Namely, to do this reduction, we now have to walk the body of the abstraction twice. Once to do the instantiation, and once to actually reduce the things we got from the instantiation. And as you can guess, walking through the term twice is inefficient. So is there a way to make this implementation more efficient? Well, more than that, I'd like it to be more efficient in a sneaky way. What do I mean by that? Well, this is the code we have for the evaluation. And as I said, it solved all of the issues I had at the start with the first implementation. So I'd rather not change this code. Of course, performance is not going to improve magically. So if we don't want to change that, well, we do need to change the other piece of code we had. And here, we can reuse the same trick we used in the first implementation. There, whenever we had one of these abstractions, rather than walking through the body and applying the substitution, what we did is that we packed them together and returned the whole thing. And we can pull the same trick. Oops. In my bind type, I will add a substitution, a delayed substitution, which means that in my subbind function, rather than taking the substitution and applying it outright as we did before, we can now instead take it and stash it in this brand new field we've added in our bind type. because we might have already stashed another substitution there, we actually have to fuse the two of them using this funny operator, but no actual work is getting done. And it's only in the instantiation function where I have to walk through the body of the binder anyway to replace the binder by the value we're instantiating it with, that I will do all of these substitutions I've fused together and the instantiation all at once. So, and as you can guess, doing this fusion is more efficient. So, of course, up to this point, I've been kind of hand-waving about performance, what seems more efficient, but we can benchmark this. So we're going to benchmark our 3 implementations. Of course, we need a benchmark, and we're going to use this big term known as Lennard's term. Fundamentally, it's doing a lot of natural arithmetic using church numerals, so as you can guess, many beta reductions are going to happen. The first implementation of the interpreter is really fast, 0.2 milliseconds. However, our second implementation with the substitutions is super slow, 3 whole seconds. The silver lining, though, here is that just by delaying substitution at the level of binders, as we've done in the last version, we're back to 0.7 milliseconds. So this is still slower than the first implementation, but we're getting all of the benefits, and we're in the same ballpark. And this is my first takeaway from this talk, namely that if you are to implement something based on these naive substitutions, delaying them at the level of binders can improve performance dramatically. So up to this point, I've been talking about an implementation of the lambda calculus, but a good implementation doesn't make for a great library. So the first question I want to answer now is, can we actually turn this idea into an actual library that you and I can reuse for other things? The second question is, well, if you were to use a library to handle variable binding, you might expect a bit more from it than just binding variables one by one. So does Rebound offer a few more features? So regarding my first question, this is all of the code we've written for the last implementation this far. And the game is going to be to see whether we can factor it into client code on the left for you and library code on the right. So here, all we have to do is first, we're going to fault eval because it's taking a bit too much space. Then we can turn this subst function, whose implementation is very specific to the lambda calculus, into a type class, moving the implementation to the side of the user. And the last thing we have to do is change the library so that it can work for any type of terms, not only the lambda calculus, but here we just have to abstract over this type. And we're already done. And here, I'd like to take a minute to contemplate what we have. On the right, we have this library code, which handles variable binding, and uses these delayed substitutions for performance. On the left, however, we have this implementation of the lambda calculus, which crucially did not change from the first implementation based on substitutions we had. And what that means is that it does not know about delayed substitution, nor does it need to know. And this is a key design choice of Rebound, namely, the main APIs of the library do not expose delayed substitutions to the users. We do still offer some lower level APIs, because manipulating a delayed substitution explicitly can be useful at times, but these are not the main APIs of the library, which completely abstract delayed substitutions away. So now let's talk about some additional features. If you were to implement something a bit more complicated than the lambda calculus, let's say the lambda calculus with pairs, you might want to bind things which are a bit more complex. As an example, up right here in the object language, we have this binder where it is binding 3 variables at once, and more than that, it's binding them according to a nested patterns of pairs. So Rebound allows you to easily implement that in your syntax. All you have to do is first declare a data type to represent your patterns. So in our case, we have 2 different kinds of patterns, single variables and pairs of subpatterns. The type is once again indexed by a natural number, but this time this number is here to track the number of bound variables by the pattern, meaning that the variable case is a pattern of 1, because it binds 1 single variable, and a pair of patterns has to bind as many variables as the sum of its two sub-patterns. Then, in your abstract syntax, you can use this slightly more complex form of the bind type, which takes a whole pattern, and meaning that you're binding the whole pattern all at once. And this way, Haskell's type system is going to be able to statically tell you that whenever you're working in this term T2 on the right, you have m plus n variables, the m being bound by the pattern, and the n variables which are free in the overall term.
Is pat the same as pattern?
Did I? Yes, I did mess up. I forgot to rename all of my occurrences. Thank you for pointing that out. This should be pattern as well. My apologies. So, sorry, what?
What's the if there?
Sorry, I did not get that.
EFP after bind.
This is the type we're binding in. So we're binding an expression. So, oh yes, I see what's the issue here.
The XP is unbound.
Oh, that's a very good catch. I made two mistakes here. Oh, rather I made two mistakes. I named pat instead of pattern, and x should be tm. My deepest apologies for this scarfuffles.
Tm of n or tm of n?
The n is right, yes. So here, this kind of patterns is enough to support arbitrary data types and pattern matching in your object language. And those of you who are familiar with dependent Haskell might be wondering about how hard does it get to program when you have these type-level operators such as plus involved. And our answer to that is yes, internally, and by internally I mean in the library, things can get a bit hairy or complex to get right, but it's more than manageable, and this complexity doesn't really leak to the users. So we think this is fine. If you're interested in more details, please check the paper. So another thing is that the Bruijn indices are great internally to bind variables, but they make for terrible surface syntax. I think that all of us will agree that writing code like the snippet on the left doesn't sound pleasant. And worse than that, if you are to ask your users to write code this way, and they make a tiny mistake and you spit back this error message here, I don't think they're gonna stay your users for very long. So here what you should be doing is that you should allow your users to use source level names, let's say string, map them to the Bruijn indices, and whenever you want to speak back to your users with error messages, you should translate back. Here, I assume some people are going to scream reader monad, and you would be right. The only issue is that if you really want to leverage all of the type information we have, the reader monad is not going to cut it, because you're going to run into issues due to the indices we have in all our types. That being said, Rebound offers a slightly more general version of the reader monad, which is also indexed, and this allows you to get all of this implemented very easily. So, now I've talked about Rebound the library, but there is one last question about it. Is it actually any good in practice? And I want to explore two different questions here. The first one is whether it's expressive enough. Can you implement interesting calculi using Rebound? And the second one is performance. In the very first part, I've showed you that the ideas seem to be efficient. Is it actually in practice when you start implementing more things? So, regarding the first question, we've implemented many different calculi using Rebound. The list is on the left, and the, let's call them features used by one or more of these calculi are listed on the right. And of course, all of these examples are self-contained, documented, and available on our GitHub repository. I just want to quickly highlight one of these features on the right. It's going to be the very last one. People here who have implemented the substitutions before know that this subst function we had to implement before can be a bit repetitive to implement. And Rebound actually can derive this implementation for you if you use something called generic programming. So, as a bigger case study, we've also re-implemented pi-forall. That is a dependently typed language which is used to teach people about dependent types. And a few features of this language include dependent data types, which means again, for the people knowledgeable about dependent types, that Rebound needs to support telescopes, and it does. It also has dependent pattern matching. And finally, it uses source level names, which means that it puts the reader mode that I've mentioned before to good use. Another interesting thing about pi-forall is that the original implementation was already written in Haskell, which means that we can actually compare the two implementations. And it turns out that our Rebound-based implementation is more performant than the original one, both in terms of time and space. If you want the actual numbers, once again, please go check the paper. Finally, we can compare Rebound to other libraries for verbal binding in Haskell. So we'll have 3 benchmarks here. The first one is going to be this eval one, which reuses the Leonard term that I've showed you in the first part, and it asks every implementation to reduce the term to a value. The second one, NF, is a variant where rather than evaluating the term needs to be fully beta normalized. And the final benchmark, random 15, is a collection of 100 lambda terms, which all need to be fully normalized. So our baseline is going to be the Rebound-based implementation. And we can see here that the 2 Leonard benchmark take roughly 4 milliseconds, and the random 15 benchmark is faster, taking 0.5 of a millisecond. So the next 2 implementations use the Unbound library. And quickly, Unbound also offers these generic programming features I've mentioned before. And we can see here that they have a negative impact on performance. But regardless of whether you use that feature, we can see that this implementation is a lot slower than the Rebound-based one. The next contender is Foil. That library is based on the idea of the rapier, which is itself used in the GHC compiler. And interestingly enough, this implementation is faster than Unbound on the 2 Leonard benchmarks, but is a fair bit slower on the random 15. But nonetheless, slower than Rebound. The last contender is the Bound library, which is also based on the Bruijn indices and uses this idea of, and I quote, making it suck less to make it more efficient. And here it is a bit more efficient than Rebound on the 2 Leonard benchmarks, but is slower on the random 15. So that could be the end of the story. You win some, you lose some. We're more or less on par with Bound. But there is one last thing. I did mention earlier in the talk that Rebound also offered lower level APIs, which allowed you to manipulate delayed substitutions explicitly. And you can actually use these APIs to re-implement these evaluators. And if you do that, you get an implementation which is faster on the random 15 benchmark by a slight margin, but is way faster than every other implementation on the Leonard benchmarks. And even if you use the generic programming to automate some of it, which again slow down your implementation, you still get pretty good performance. So that will be it for this talk. Maybe one last thing I did not have time to talk about, which I think is interesting. I left environments abstract throughout this talk, and there is an interesting conversation to be had on how do you represent and optimize these environments. And we talk about it in the paper, so if you're interested, please check it out. And that's it for me.
Thank you. Of course, we have time for questions.
So you stressed the idea of delayed substitutions.
Yes.
And that when you do eval, instantiate followed by eval, you're going to kind of fuse them.
Yes.
That was but there's a bit you're sweeping under the rug there because you only make the delayed substitution at a binding. Right, so
yes.
if you've got a big tree of applications,
yes.
then you're going to eagerly instantiate and eagerly eval.
Yes, very much so.
But I think that's a very clever compromise.
Yeah.
Right, so you've got a hook in abstractions.
Yeah.
You didn't really highlight that at all. I think that's the clever compromise that Rebound does.
Yeah.
Is that right?
That's right. So there are 2 things going on here. The first one is, as you said, the bind type is the one type which is not implemented by the user, which means that we can smuggle the delayed substitution at that level without the user knowing about it. The other thing which I did not talk about in this talk, which I think is interesting, is that there is this idea of explicit substitutions. I think that's the right name, where rather than doing this whole thing where you hide substitutions, you make them explicit in your calculus. You add a new constructor to the lambda calculus with substitutions. And we did benchmark it, and this was slower than Rebound. So from going into, or rather profiling that implementation, it seems that if you do that, you end up spending way too much time allocating and garbage collecting everything you allocate. So hiding things at the level of binders has these double benefits that you don't do it all of the time, and we can hide it from the users.
So it seems like quite a clever design, because partly you can hide it from the users, because that's the one type you implement. But also, you sort of chunk it up. So instead of doing a delayed substitution every node, just when you get to an abstraction, and typically abstractions show up quite a lot, but not absolutely. Very, very nice.
Thank you.
Are any of the approaches you benchmark against, non-intrinsically scoped that can tell you, how much overhead is caused by intrinsic scoping?
So here, Unbound is not intrinsically scoped. So sorry, can you ask the second part of your question again?
I'm just wondering how much overhead is caused by intrinsic scoping. So I'm wondering if you compare it with any approach that is not intrinsically scoped that can tell you that.
So my impression of this whole thing is that the part about being intrinsically or extrinsically scoped is kind of independent of the trick we're pulling with the delayed substitutions. The two things are nice to have because you want performance and you want type safety, but I don't think the two of them are you can have one without the other. Actually, what's interesting, and maybe we should do that, is try to benchmark an implementation like Rebound, but without the whole scoping thing. I'd expect similar results, but maybe I'm wrong about it.
Is this like a talk? It's for all that.
Oh, see. Oh, quickly.
Yeah. You sure it's working?
Apparently so.
Okay. Have you come across the term weak explicit substitutions?
Weak explicit?
Because I think that's exactly what you're doing. And if
Oh,
you
that's
search for
interesting.
that, you'll find some literature that I
Oh.
can't remember who did it. But
I will definitely look into that. Thank you very much.
Thank you for the great talk. Can you please give some details on why do you think that the random 15 benchmark seems to behave very differently?
So that's going to be kind of a guess on my side. But the Leonard term that we've been using for benchmarking has actually been around for a while now. In fact, if you look at the slideshow used to present the bound library, they were using that benchmark as well. So what I think happens is that a lot of library, ourselves included, kind of, in a way, optimized for that specific benchmark, whereas the random 15 is, well, random terms. So we could generate other random terms and we might get different behaviors as well, slightly at least.
Okay, thank you.
Okay, we have time for one more quick question, I think.
Yeah, it's a very quick question.
Yeah.
Is it you mentioned that the explicit substitution calculus implementation is slower?
Yeah.
Is it like a publicly available, the implementation?
So we do have that in the paper. So if you want to see the implementation or the numbers, they are there. Yeah, I don't really have anything to add to that.
Okay, thank you to the speaker.